In this video, I am going to discuss about exact equation. So the first order ordinary differential equation looks like dy dx equals f of xy. Now this equation can be written in many different forms. For instance, let f of xy equals negative m of xy upon n of xy. M and n are functions of x and y. So 1 becomes dy dx equals negative m upon n, or n dy equals negative m dx, or m dx plus n dy equals 0. This is another form of the first order ordinary differential equation, and this equation is said to be exact if there exists a function g of xy such that m dx plus n dy can be written as dz. That is, derivative of z is nothing but m dx plus n dy. So now consider examples. First one, x dy plus y dx equals 0. Is this an exact equation? Exact. Answer is yes, because the left hand side, that can be written as d of xy. So here g is nothing but xy. Example 2. Suppose 2xy square dx plus 2yx square dy equals 0. Is this exact? Answer is yes, because the left hand side, this can be written as d of x square y square. See, the d of x square y square nothing but this can be written as x square. Apply UV rule, we'll get first x square, then derivative of y square, that is 2y dy, plus y square times 2x dx. Okay, now the bigger question is there any tool to check exactness? Is there any tool to check exactness? Answer is yes. We have a theorem, and that is a necessary and sufficient condition. The theorem says m dx plus n dy equals 0 is exact if and only if del m del y equals del n del x. The first equation is y plus x dx plus x dy equals 0. So this is our m and x is our n. Now del m del y is nothing but 1. The derivative of y with respect to y is 1 and the partial derivative of x with respect to y is 0, therefore this is 1, and see del n del x is nothing but 1. So these two are equal, so the given equation is exact equation. Number 2, y plus x square dx plus x dy equals 0. This is also exact equation because this is our m, this is n, and del m del y. So partial derivative of y with respect to y is 1 and 0, that is 1, and del n del x is nothing but 1. These two are equal, so therefore this is exact. Now consider another example. x square minus 4xy minus 2y square dx plus y square minus 4xy minus 2x square dy, this is equals 0. So this is nothing but our m and this is nothing but our n. Let's calculate del m del y. So the first one will be 0 because derivative of x square with respect partial derivative of x square with respect to y is 0, and then treat x as a constant here, so negative 4x and then negative 4y. On the other side, del n del x, this can be written as 0 negative 4x and then negative 4y. Y will be treated as a constant and the derivative of x is 1, so negative 4y and negative 4x because 2 times 2x, that is 4x, and see these two are equal, so therefore we can say that this equation is exact equation. Consider another example. Let's say y dx negative x dy equals 0. Now check, this is not exact equation, not exact because see our m is y and n is negative, n is negative x, m is y, so del m del y is 1 but del n del x is negative 1. So these two are not equals, so therefore this is not exact equation. Now if an equation is not exact, we can make it exact by multiplying some function. See, if we multiplying by 1 upon y square, what we will get, we will get y dx minus x dy upon y square. This is equal to 0. Or we can write this as d of x upon y. So this is nothing but d of u upon v. So we can easily write this as b square b du minus u dv. So similarly here, this is d of x upon y, and this is nothing but exact equation. So we had non-exact equation, and we multiply the whole equation by 1 upon y square, and we got exact equation. And this 1 upon y square has a special name, that is integrating factor. Integrating factor. So what is integrating factor? Suppose m is a function of xy dx plus n is a function of xy dy equals 0. This is a differential equation, ordinary differential equation, and it is a non-exact equation. This is not exact equation. So by multiplying, let's say h of xy, the equation 1 can be made exact. Then h is called integrating factor. Now let's see how to solve an exact equation. So let's say m dx plus n dy equals 0. This is exact equation. So the left hand side, this can be written as dz. But the total derivative of g, is dg equals del g del x dx plus del z del y dy. So if we compare these two equation 1 and 2, we will get, because this is nothing but equals to dz, and here dz equals these things, so we can easily compare this, and equivalently we will get that del z del x equals m and del z del y equals n. Okay, integrating with respect to x, we will get z as integration m dx, and we have to treat the y, treating y as a constant, and similarly we will get from the other side, from here we'll get z equals m dy, and we must treat x as a constant. So we have two z's. So compiling these two, we will get that z equals some constant is the solution. This is solution. Now try to solve an example for better understanding. Example: x square minus y dx plus y square minus x dy, this is equal to 0. See, this is our m, this is our n. M, n. Del m, del y will get 0 minus 1, that is equals negative 1. Del n, del x is 0, partial derivative of y square with respect to x is 0, minus 1, that is negative 1. So these two are equal, therefore the equation 1 is exact. Okay, since the equation 1 is exact, so there exists a function, let's say phi of xy, such that the equation 1 can be written as d phi equals 0, or phi of xy equals c. C is nothing but the integrating constant. Integrating constant is the solution. But d phi is nothing but del phi del x dx plus del phi del y dy. So del phi del x is our m and del phi del y is our n. But we have m is x square minus y, so let's put it here, x square minus y, and on the other hand n is y square minus x, so n is y square minus x. Now integrating with respect to x, treating y as a constant. So here y is constant because we have the partial derivative with respect to x. So phi can be written as integration x square minus y dx. Okay, then we will have x cube upon 3, and negative y is constant and integration dx is x. On the other hand, we have to integrating with respect to y, treating x as a constant. X as a constant, we will get phi equals integration y square minus x dy. So y cube upon 3 negative x times integration dy is y. Now see, we have a common term, that is negative xy. So therefore phi of xy, combining these two, we can see that phi of xy can be written as x cube upon 3 plus y cube upon 3 negative xy. So therefore we have the solution phi equals c. Now solution of the given exact equation is x cube upon 3 plus y cube upon 3 negative xy equals c, where c is the integrating constant.